With cyber attacks on the rise, creating software that's secure is critical to every business's success. Yet 50% of organizations provide developers with security training only once a year, and much of this is often boring, unengaging, and not relevant to your everyday work. Veracode Security Labs offers real-world, hands-on challenges that gamify secure coding and put your skills to the test in as little as 5 minutes. You can select from dozens of interactive labs and the most popular programming languages. You can compete with colleagues and get instant remediation guidance, all at your own pace. Visit veracode.com/labs, that's VERA, code.com/labs today. You can start hacking and patching real apps right away with their complimentary community edition. Friends, I'm Scott Hanselman, and it's another episode of Hansel Minutes. Today, I'm talking with Dr. Jean Yang. She's the founder and CEO of Akita Software. How are you?
I'm doing well. How are you?
I am living the dream. I am avoiding the snow here in Portland, Oregon. I hope you are safe and well.
Yeah, it's very sunny. I had to put the blinds down. It's so sunny.
Well, now you're just showing off. The rest of the world is buried in snow right now.
Sorry.
That's okay. So you have a PhD from MIT, and you also did some postdoctoral work. You taught as a professor, but now you're the founder and the CEO of Akita Software. And it's interesting. I'm curious, whenever I have a PhD on the show, I always read their thesis because I want to understand kind of like where they're coming from. Oh my gosh,
I'm sorry.
That's okay. I have since learned, though, that a PhD's thesis does not always represent like their identity or their worldview forever. It's your worldview at a moment in time. Is that a correct statement?
Oh yeah, absolutely. It's kind of like I wrote it when I was like, 25, 26, however, 27. I don't know. It took a long time, but it's I've learned some things since then.
Mm-hmm. And when you do that, do you ever look back on a theory that you had? Because it is a theory that you're then trying to prove. It's a postulate that you're saying, here's my thesis, here's how I think about a thing. You then defend it. Do you look back now, years later, and go, "Oh, that was not the thing at all"?
Yeah, I think one way to look at everything I do now, it's in response to what I spent years of my life doing. Because I did my thesis in programming languages, and one way to look at a lot of programming language design theses is what you're doing is you're saying, imagine if the world looked like this, and then you spend 5, 6, 7, 8, 9, 10 years living inside that world. You flesh out the entire world, and you're like, all right, I've been living inside this world for 5 to 10 years. This is what it looks like. This is what it would mean to live inside this world, and there's usually a question at the end, which is, should other people live inside this world? And my answer to the entire approach I took to my thesis was no. I lived inside that world for a bunch of years. I'm good. Everyone should just move on. And I can explain more what that means, but basically for my PhD, I was designing a new programming model, and what that means is you say, well, let's say your programming language could do something for you. Wouldn't that be nice? You would live in this nice world. All these things would just be done for you. And I discovered many things along the way that made me realize that I don't think programming languages are the way to solve many of the problems that I see in programming today.
Interesting. I have found in reading many theses and talking to many folks that there is here's a survey of the landscape as we see it. Here are the limitations of the landscape that we see it. And then here is a new paradigm, a new way of thinking, and a series of constraints that we could impose upon that landscape that might then make us go to the next step, the next level, the utopia or whatever, or at least move up a step as we move towards things getting better. It seems to me like you were trying to apply constraints to a system that you saw to be somewhat willy-nilly. There's like a lot of limitations in existing frameworks and information leaks and the security problems. And you're saying in the past, you could solve that maybe with a new programming language or a new paradigm. And you think that maybe that more strong types and more static analysis is not the way to solve the problems of the world?
Yes, I think so. And here I can tell you about my entire thinking. So this is what happened. I started my PhD because I had let's rewind to the beginning of my life. So most of my family who's close to me is computer scientists. In fact, like all of my cousins except for one so far, and the one who hasn't finished college studied computer science. We're a lot of computer scientists. And so, I grew up programming. Everyone used a lot of
It must make
computers.
Thanksgiving dinner very
Oh
exciting.
yeah, it's they all think what I do is extremely boring. They're all into AI and stuff, so it's just like the rest of the field. But I grew up programming. I never really knew if I would end up doing this for a living. But junior year of college, I took compilers, programming languages, and hardware, and I was like, man, no one ever told me that you could actually build the tools to really shape, this is how stuff gets made. And that's really what got me hooked. Because I was like, we've been using suboptimal tools this whole time, but I can fix it. I can make programming more fun. I can make life better for everyone. It just seemed like the thing to do. And so, as people who fall in love with programming languages are wont to do, I learned Haskell, I learned OCaml. I was like, man, it's so nice to have static types. I just, eliminate whole classes of errors. It's pretty much, whatever my programming languages professor taught me, I just ate that up. I'm like, wow, this is amazing. You should check everything at compile time before you run the program. And, I like what I want to do is design the next language. So the way I thought about what I wanted to do was the same way garbage collection just revolutionized the way, the accessibility of programming and the ease of programming and just whole classes of bugs that people did not have to worry about. I was like, what's the next thing? And so that's how I got into information flow security policies, because I was building web apps and I'm like, man, and all these web apps, like 90% of the hard code is like making sure the right checks get put in the right places. And so I was like, cool, maybe I can build a language to automatically enforce access control and information flow in these complex systems. And, this seemed very reasonable to me at the time. I feel like there's some things that I thought that were pretty prescient. I was like, this was the late 2000 zeros. And so I was like, Facebook is going to be huge and there are going to be massive problems with privacy. And, last few years, I'm like, haha, I was right. Like nobody thought I was right back then. But then there are some things that I thought that it was a learning process that I no longer agree with. And so the biggest one is what I told you earlier, Scott, which is that programming languages are the way to solve this problem. And so I built this new programming model. I'm like, well, if you just bake this into the programming model, all data just has a policy attached, and then enforcement is just baked into the language. And so my whole PhD was about like, how far can we take this conceit and what does it really mean? And so I took it a little bit far. I designed a new programming model. I extended the lambda calculus to, describe what the model meant. I proved some guarantees. This is what it means for the access policies to be like fully enforced everywhere. And then I implemented this programming language as an embedded domain specific language. So as like a library that rewrites your code basically. And then I was like, all right, time to build web apps because this is why we did this thing. And so like day one of building the web apps, I start needing to make database calls. And I was like, oh no, every single one of my guarantees that I set up in my language gets completely subverted when you make database calls. And so I guess for people who aren't intimately familiar with how web programming works, like usually in web apps, you have your application code. So that's like written in some backend language that you're, like Java, Python, Scala, whatever your favorite language. And then you store your data in a database. And so you can imagine like any types you actually have in your language, they don't get automatically enforced when it goes across to the database. And so then if you have additional types like security types built in on top of that, they really don't get enforced when you call out to the database. And I was like, oh, this was really an oversight by me because all of the papers I read were like, well, if you design your language right, you get all the guarantees. And so, one third of my thesis was actually about this is how we extend our language to SQL databases. But then like I played this out a little more and I'm like, all right, so there's SQL databases, there's no SQL databases, there's graph databases, there's all kinds of databases. I can't spend, 20 more years extending this to every kind of database. So that was one problem I ran into. Another problem I ran into was the way I was enforcing these policies was dynamic. So it was at compile time. And I was like, man, this is really causing some overheads because I have to check a bunch of stuff all the time. I'm propagating all these policies all over the place. Maybe we can do it compile time or statically. And so one of my next papers was, this is how we have really fancy types, and then check those types. And then we can like rewrite your program to put the checks in. And I was like, cool. So this worked for like a fancy Haskell like language. But then I was like, well, no one's using this stuff. Everyone's using JavaScript. So then I spent like over a year trying to add like these fancy types on top of JavaScript so that we could one day rewrite JavaScript. But basically, like I took the core of what I did for my thesis and I projected out like, this is all the things we would need to make this practical. And I was like, that would be the rest of my human existence, that I would be like doing all this stuff. And, you know, then there's like all the runtimes that are out there. No one's modeling the runtimes. And so so essentially I was like, okay, I think that if we're to solve this problem, it's sort of like, I don't know like how much philosophy people have read, but there's some philosophers that are like, you know, we will model the world starting from like atoms. And then they get to like, this is what it means to be like a tree branch. And then like, you know, you're just like, wow, you're so far away from modeling the complex dynamics of human societies because you're like modeling tree branches. That was kind of how I felt about like the like line of reasoning that was starting off from my PhD thesis.
It seems like when I teach people how to use computers, that if we go too far down, we lose ourselves in the layers of abstractions. Like one of my favorite questions to an interview person is, you know, tell me what happens when you type google.com and you press enter. And then you always get that one kid that's like, well, the enter key touches the metal of the in the keyboard, and then like the electrons jump between. It's like, whoa, like I want you to model what happens when you press enter. It's like, well, yeah, but let me talk to you about the rock that we taught how to think. And then suddenly we're thinking about the quantum state that's happening inside of this x86 or x64 processor.
Yeah, you're just never going to get there.
You got to let go at some point. But what you did is you're also going up the stack and saying a generalized programming language can call out to devices and sensors and APIs and all these kinds of things. It sounds like you kind of standardize when you get towards your product on, we're going to call web APIs, and that's really inter-process communication. It's RPC in the 2020s.
Yeah, absolutely. So I had this, as you can imagine, years-long existential crisis towards the end of grad school where I was just, you know, modeling more and more things. And I was like, man, this is it's getting to be a lot of work and I'm nowhere near done. And so at some point I was like, there's got to be a better way. Because, you know, I started thinking about all the runtimes and all the things and, you know, RPCs became a part of it. And a fun fact about me that I remember today is I actually wrote my senior undergrad thesis on how to use, this is going to be like very specific, but how to use this construct in Haskell for doing type stuff, type classes with type dynamic, which is the type representing any type. And my motivation for my entire thesis was sometimes you got to call across the network. And so you can see from like a pretty young age that I was always like, but what about when you call across the network? And so at some point early in my time when I was a professor at Carnegie Mellon, I got this grant where people wanted me to enforce policies, but they're like, we can't show you the code, so you have to do it at the API level. And I was like, API level, huh? And this is how I started realizing that the API level is great, because they're like, we have this back end, we have this front end, it talks to each other through this API, it's a REST API. And then I looked more into it and I was like, whoa, this is pretty standard. REST APIs happen a lot. And even if you don't just have a REST API, there's really good standardization around different APIs. And so this paper I did as a result of this grant was we looked at how do we do language agnostic black box enforcement of these data security policies at the API layer. But I got very hooked on the API layer because I was like, man, this is so much more general and solves all the problems that I was struggling with before.
Interesting. So it sounds like in trying to model the world, and you're thinking about molecules and atoms and stuff, you're like, okay, well, this is atomic. I'm going to break that apart. Now this is the atomic. You reasserted and kind of like re-leveled everything. Okay, well, if the new atom is the API level, you can basically abstract away and literally pretend that the other bits don't exist. Because looking in your career here, it seems like you were kind of obsessed with verification and strong typing, all throughout the early 2000s, and you worked on, Verve, the operating system that was verified end to end for type safety. You want to verify things at the quark level. You just kind of spackled over the top of that whole thing. Like, okay, APIs are the new atoms.
Yeah, absolutely. Services are like the atoms. And this is actually a lesson I learned from Verve. So Verve so this operating system I worked on, if this is getting too detailed, you can just make me stop. But one of the holy...
No, this is good stuff, and I'm going to include links in the show notes to all this stuff because people love it.
Cool. So yeah, one of the holy grails of proving the correctness of computer systems was proving the correctness of an operating system, because it's a large system. Everyone uses them, and everyone knows that they're very, very hard to model and prove correctness about. And so a lot of the work on proving operating system correctness had been like, let's start with proving the assembly code under the operating system correct. And then let's prove the C code correct. And there's a paper that came out at the same time as the Verve paper that took 30 person years, huge. It's called SEL4. So it's the secure version of the L4 microkernel. But, that was just a feat of human engineering that they spent so long doing that. And the Verve paper came out of this alternate tradition. So there was a project at Microsoft called Singularity that took this idea of, what if we wrote an operating system in C#, which is type safe to begin with. And they got pretty far, but not completely far, because as with most language-based approaches, you get subverted at some point. And so just like how I kept getting subverted by non-language calls, when you're building an operating system, you get subverted by the fact that your operating system needs to move the stack pointer, it needs to set up memory, and it needs to do all these type unsafe things. And so what happened with Singularity was you have all these type unsafe calls, like unsafe call, like whatever. And so you actually don't get type safety across your operating system anymore because you got subverted. And so the whole idea behind Verve was, can we quarantine all the code that doesn't have to be type safe? Then we put a barrier up to the type safe code. And so most of the previous efforts to prove type safety had been like, let's prove the assembly code is type safe all the way through, then we'll prove functional correctness on top of that. But what we showed was, this was basically an internship project for me. It's 3 months of an internship. We took this low level, the tiniest kernel we could possibly have that is like not in C#. I wrote that. I proved that it adhered to basic type safety guarantees. And then we're like, the rest of the operating system should just be in C#, and then we're good to go. And so it was a total 9 person months project as opposed to 30 person years. And to me, that was just like, okay, whenever you get subverted, you should try to quarantine the stuff that you can't control as much as possible, and then get yourself an interface that you can work with and just like lift yourself into a higher level. And so in some sense, the API stuff we're doing now is exactly the same thing. It's like, all right, we got subverted by always having to call stuff in a different language. How can we wrap that and have interfaces that are kind of airtight? And to me, those are like REST APIs, gRPC APIs. Those APIs are another way to kind of lift your level of abstraction up and just take all the stuff that's messy and just put it in an atom, as you said.
Tired of not finding the code you're looking for? Get SourceGraph Universal Code Search and search code across your entire code base. That's all your repos, languages, and code hosts. Find and fix bugs, do better code reviews, identify security risks, onboard to a new code base, and make large-scale refactors. With SourceGraph, you can find anything in code fast without losing your flow. SourceGraph Universal Code Search is a developer's superpower. Try it now at info.sourcegraph.com/Hansel-minutes. That's info.sourcegraph.com/Hansel-minutes. So, as with all layers of abstraction, you're having to make assumptions. You are basically letting things go, and you're assuming that things are correct on lower layers. It's turtles all the way down. There are API proxies, interception layers, and things like that. There are things that make you feel like you're talking to an API, but you're really talking to a proxy that's going to check everything. Are you intercepting everything? Is your plan for making APIs correct to stand in between as a gatekeeper?
Yeah, that's a really good question. So right now we don't do that. So I have come to learn many hard-earned lessons over my period of time of trying to make software tools better. One is that there are two operating lessons of what we're doing. One is that you always need to meet people where they are and like as least invasive of a way as possible. And the second is that everyone would like to have specifications, but no one actually wants to create them. And so my operating assumption of the state of the world is no one really quite knows what's going on, and no one really quite exactly knows how to express, or no one really wants to take the time to express most of the time, unless you're designing like a rocket ship software, what should happen in gory detail. And so what we're doing at Akita now is actually just helping people characterize what their software is doing, and we're less invasive than a proxy now. We're doing it with PCAP filters, so like network sniffing. We just listen. So we listen to what's happening across the network in integration tests, what goes to the APIs. We build our own model of this is what we think the interface is, so we don't require anybody to write anything. So along the way, we also generate auto updating API specs that people can use for other purposes, and then we use these models to help people do whatever they want with their APIs. They might want to understand what endpoints they have, what data is going through those endpoints, what data formats they're using, or things like that. The bigger thing that people seem to want to know is, did anything break based on things I did? And so the breaking changes problem turned out to be one of the bigger reasons people were showing up to our tool. But it goes with my general learning that people don't seem to want to know, like they don't want to understand what's going on necessarily, but they want to know enough to know if anything broke. And so one way to think about what we're doing is we're building these models underneath that they could or could not look at. They could use these models to spit out API specs to show other people. But the big thing that we think is really, really cool is we can help model change over time and communicate like this is how your behavior changed, this is what you might want to pay attention to, and it's using like very related underlying principles. Like if you model a system based on first principles, or if you're inferring that model, it's still a model. So it's using very related things to what I worked on, but it's just going the complete opposite direction in some way, and at a higher level of abstraction up.
So your system knows about these API specifications that are standards, which means that it'll work on any language that can produce an API spec, because the API spec is the intermediate language, right? It's the new assembler. Open Web API is the new assembly language for the web in this context.
Yeah, that's perfect. Exactly.
Okay. You've got these endpoints. The API specs go through versioning experiences. They change. They are either formally versioned because you're a really organized company and you're great, or you just flat change the interface because you're sloppy. You have this concept of witnesses. What is a witness in the world of Akita Software?
Oh yeah. So for us, I guess like I love you calling API specs assembly, because that's exactly how we think of them. And so what we're essentially doing is we're watching API traffic. We're creating request response witnesses out of them. And so we started doing this because people didn't want us to see their private data in the cloud, but we basically like abstract out the sensitive data in a request and response. Mm-hmm. And then those abstracted traces are what we use to build models, which one way to think about these models, and I don't know how compiler geeky your audience is, but we think of the models we build as like an intermediate representation for API behavior. And so like LLVM is an intermediate representation. The CIL for .NET is an intermediate representation. We see that, and those are intermediate representations that compilers use because they generate regular assembly. We see what we're building as an API intermediate representation that generates API specs. And the witnesses are the traces that we're using to analyze what's going on to generate that.
It's interesting to think about something low level like C calling assembler or C calling syscalls in Linux, and me tracing them and watching that, and the opcodes are very low level. And then it's almost no disrespect, and I hopefully don't get the word wrong, but like it's almost insane to think about a web API as an opcode for the internet itself.
Oh yeah,
It's just a very brain warping thing to think about.
it's totally insane. Yeah, because it's just so many levels of abstraction up. It feels so much messier, and
You're
I think
standing on
that
50 years of internet.
yeah, yeah. And something I learned fairly recently was, it was not inevitable that there was so much standardization. And so the fact that there are really, a number of different protocols that you could count on one hand that you really need to worry about was, there could have been like 50 protocols, which is pretty cool that it happened the way it did. But yeah, I think many people tend to think of assembly as ground truth. It's not something you can change, and it's it's what runs on hardware, versus API specs are things that people write. They're not necessarily tied to code. Blah 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 blah. But the thing that I like, the different way we're looking at this is basically API specs are our way of like summarizing what we saw in across the wire. And so like we want that to be a new kind of ground truth for the internet, or for software that runs on the internet. Yeah.
I always love an inappropriate and ongoing extended analogy. So now the witness goes to the sketchbook artist and it's like, this is what I saw. And then you've got the whole thing specified in this web API. Now web APIs come and go. Like, you could have done all of this in WSDL and SOAP. You could have done all of this in COM and IDL. An interface description language is an interface description language. So if another one comes in the future, the same concepts apply.
Yeah, exactly. These interface description languages historically have not been seen really as sexy or ground truth, but that's something we want to help change, because like I said, apologies out there to everyone who loves these IDLs. I think they're very cool too, but I think that previously like these weren't really thought of as necessarily executable or like having like necessarily a big connection to the code. And there's a lot of other work out there that is connecting interface descriptions to the code more, connecting specs to the code more. And the way we look at them is it's a way to communicate not just with other people, but also with automation. And that like that's something that we've seen change, and we want to help change as well.
I've spoken to people about run books on the show and about different things that are like pieces of paper that have prose that describe systems. And many years ago, I wrote a verification system in PowerShell that basically took Word documents and used them as code. So the business person wrote a Word document.
Oh, amazing! I love that.
So the idea, the word that we used, the hook as we sold was like, your Word document has no teeth, right? Your Word document can't break the build. And we always believe that the strongest thing that you can do in a large system is break the build, because by breaking it, you prevent it from going live into production.
Yeah. No, that's a great way to describe it. And I think that that it's really related to a shift in thinking I've had through the course of doing my thesis. Because I think my PhD thesis was very much about me being enamored with executable specifications. So if you specify what you want to happen to the data, you should be able to just execute that. And I think that now I realize, well, most people, they don't even know what the specification is. They don't even know what the software is that they're running. And so now I've turned that on its head. And a lot of what we're doing now is about getting specifications from the execution. And I believe that once you have those specifications, you can execute them, you can do things, you can see if they change. You can, they have teeth now, but yeah, like it's the question of how do you actually get specifications, or how do you know what your execution is doing, is something that's always been very interesting to me.
That's interesting, because people think that their code is an expression of intent. People think that their IDL, their interface description language, their open web API is an expression of intent, but ultimately their intent means nothing. What actually happened on the wire is what actually happened. Thereby, we can infer their real intent and say, well, you thought you intended this. You put it in production. You did a canary deployment. Turns out your intent meant nothing. Reality was this. Here's the actual specification as you work backwards. And we have witnesses to prove it.
Yep. Yeah, exactly. And yeah, there's something I've started saying, which is there's no truth. There's only what happened. And And also, like, a lot of what we're working on is characterizing what happened over time. So there's no truth. There's just what happened today, and there's what happened yesterday. But this is something it's been a 180 from my original views on software, which is, you write the spec, then you write the code, then you prove that the code adhered to the spec, or the next level is you write the spec and you can just execute that. It's like, no, stuff happens. Stuff happens because of interactions with other stuff. No one really knows what's going on right now. Everyone's just throwing up their hands and saying, well, when things catch on fire, we measure like how many alarms the fire was. And so my new view on all of this is, look, like, you can still apply structure to that, but it's just the specs go the other way now. Yeah, like you're there is truth. You just have to find it.
How do we make sure that this doesn't turn into some, like, you're expecting people to just throw crappy code out the wall, and we have enough gates and rails, and we've basically put bumpers on the bowling alley to just throw the balls. Eventually, one of them will hit a strike. Like, that's not a good way to develop software.
Yeah. So I mean, I think that one way I see what we're doing is actually trying to give people understanding so that this so that they have some middle ground. Because I think that, in school, at least when I was in school, maybe I'm just very old, but they said, we are civilized now. We learn to test our code before we run it. There are things called types. And, they're like, we don't do print debugging anymore. We use debuggers. And then the minute you do cloud programming, this all goes out the window. It's logs, no tests. And it's actually very rational not to test code that's like hugely API and service based. Actually, like, this is not a knock on people who don't have tests. Like, it doesn't make sense because there's not the tools to support it. And, there aren't any types when you go outside of a single runtime anymore. And so I think that, the rational thing right now is actually to throw code at the wall and see what happens. Like, if you look at some of the best engineering shops in the world, like Canary deployments is how they're finding their bugs. Like, all of these good software engineering principles are not really being deployed when it comes to how these systems engage as a whole. And so my view is like, look, if we can actually give people the tools to understand structure at the next level, understand this is how stuff is related to each other, give them some semblance of types, give them something better than print debugging, it can only make things better. Because right now the rational thing is to just throw spaghetti at the wall.
Very cool. Well, folks can check out the stuff that you're working on. They can join the beta. They can try Akita Software for free at akitasoftware.com. You can catch breaking changes faster and learn all about the stuff that Jean and her team are working on. Thanks so much for chatting with me today.
Yeah, thank you, Scott. This was fun.
This has been another episode of Hansel Minutes, and we'll see you again next week.